Okay. Um, is there any doubt in gradient descent?
Gradient descent, no. Doubt.
Okay.
But just how it
Just
was with one variable.
just for the revision, I will write the equation. In gradient descent, what we do, we take the theta of I and we update it with this rule, theta of I, which is the previous iteration, minus alpha delta of cost function, our j theta, upon del theta. Okay, and we run it again and again, and similarly we update this theta value with this row, uh, rule, and my j cost function is 1 upon 2m summation of I is equal to 1 to m h theta m s theta I theta x minus yi
Yeah.
whole square. Okay, this was our cost function, and the first one is our descent update rule. Okay, so yesterday we saw what is with one variable. Like if I am having the house, then what was my its price? Like in house data, square feet was there, then price was there. Okay.
Yeah.
Now imagine we have for a house we have something other values also, like number of beds. Okay, number of bedroom. So here you can see now we have the two features. Okay, like if we write something, if we make some other data size, if we write then number of beds, then again what is the floors in that, number of floors, then age of house. Okay, and we take the then price value with that. So here you can see there are many variables which is defining my house. This is the property of house, like what is the size of house, how many beds there in house, what is the floor of the house, then what is the age of house, and then on the basis of that we are saying okay, this is the price of house. Now we have to find for any other one. Just take example of some two values. If my size is of this much square feet, we have the 5 number of beds, then it's on first floor and its age is 45 and 4 windows. So what we say, like this is my one data point. Okay, and so here if I am writing like 1, then 2, 3, 4, so my m will be 4 here, then how many number of features we have? Here we have 1, 2, 3, 4. 4 features. So now that's why the n will be your 4, which is the number of features.
Okay.
Okay. Now if I want to represent one training point, like one data point, how we will, what will be our notation? So like for this, like this is one our, for this we have this one as a one training data point with price. So we will write it like if we are writing only this one, this part the features of data. So for that we will write it as x of I. So here this is my first one. So this will be, this will become x of 1. Okay, now with that we have many features. So to represent that we will write it as x of I of j. If I am talking about the 2014 value, which is the size of house. So how I will write? I will write it as x of 1, and below it will be 1 and 8. For the number of beds, it will be x of 2. Okay. So, and we will use features m data point then my xi will be representing which data point. And x of I, this will represent value of
Second.
feature
Yeah.
of ith data point. So now we had the many features. So how we will write our hypothesis function? What was the hypothesis? Hypothesis was the function we want to approximate so that our data can be represented by that. So previously we used h of theta x is equal to theta naught plus theta 1 of x, because we were having just single feature. Now we have multiple features, so we will write it as h of theta x is equal to theta naught theta 1 x1 then theta 2 x2 and so on till the nth point. It will be represented from our this will become theta n of xn, and like in the previous one at this place we had the 4 features. So for this our equation will be theta naught plus theta 1 x1 plus theta 2 x2 plus theta 3 x3 plus theta 4 x4, because we have only 4 features. This is clear? Your voice is breaking.
Yeah.
Hello?
Yes, it's clear.
Yeah, okay. So, and what will be the my x1? X1 will be our size, which is in square feet. Then other feature we are taking, this one will become the number of beds. Then this one will become the age of home, age of house. And sorry, this one is age of house, and this is number of floors.
Yeah, please.
Okay, so in like if we have any other features also, it will be represented in the same way.
All right.
Okay, now like you saw that writing this complete equation will, like every time writing this complete equation is hectic. Yeah. So to simplify this, what we do, we make it in a matrix notation form. So instead of writing that complete variables, we just write my x naught. I am having the features. So my features are the x1, x values, x naught, x1 till I had xn. Okay. Now you will see what is this x naught. Okay, so what we do, like we saw here, Nimesh, just wait 1 minute, I will tell him to mute from his side.
Yes.
Nimesh,
Hello.
Can you mute from your side? There is lot of noise.
Wait.
Yeah. So how we are writing equation in our multiple variable form? We are taking x naught x1 theta 1 x1. So you can see there is theta naught and there is no any input variable associated with this. So to make to simplify this equation form, what we say, we assume that we had this x naught here, okay, this x naught here, and we assume this as a 1. So now if we are writing, so how we will write? Theta of x is equal to theta naught into 1, which can be theta naught x naught. So what I am saying, that my x naught is 1 value, because this is same as theta naught by a term, and now theta 1 x1 and so on. Okay, so now you can see here I am having the simplified one, so I can just write the x naught here at this place. Okay, and similarly, how can I write my theta? I can write theta as a vector of all the theta. So it will start from x theta naught to x theta n. Clear?
Yeah.
So, and because now we are writing it matrix form, so what we can write, h naught x as h theta x, we can write as theta of transpose x. Did you get this? How I am writing this?
No. Wait. Theta of transpose x. Oh, okay. Yes. I get it. The transpose we changed the row to column.
See, I will tell you one.
Yeah.
I will tell you, like, this is a tricky part here. My x value is till x naught to xn. Okay. And similarly, theta is from theta naught to theta n. These are the vectors. And what I had in my equation, this one was theta naught x naught plus theta 1 x1 plus till n theta n xn. Okay, so if you this is like a this is multiplication of two vectors theta and x. When we multiply two vectors, like first of all, how we can multiply two vectors, like if I am having this as theta naught to theta n, this is my 1 cross n matrix, n plus 1. Okay, because we added theta naught, it will become the 1 n plus 1, and we have
That's n into 1.
Yeah, x naught to xn, so
Xn.
it will become
N into 1.
1, okay,
Yeah.
into 1. So
Yeah.
we can multiply these two matrices.
Yeah, and then you get that result at
And
h
we
naught
will get
h theta
theta.
x.
Okay.
Yeah.
And what is my theta?
Yeah.
So what will be this matrix? This will be your theta transpose. My theta matrix is this. Okay. This is my theta matrix. So what will be this matrix? This we can write it as theta of transpose. Like if we transpose my all, here I am having just single column, so it will be converted to single. Understood?
Yeah.
Conversion of these two. Okay, so that's why we can write it as theta of transpose into x. Okay?
Okay.
Okay. So now we understood how we can represent our problem. Now what we have to find, what we have to do, we have to find these theta value. Like we know this is x, we know this is, what is this, like this is the square feet, then this will, if I am taking the same example, so this will become my, and will become my age of house. So we don't know theta, this is a parameter, and now we have to find the parameter. So as we did in a single variable case, we will do same thing here. We will apply the gradient descent in multiple variable case. Okay. So you are clear that my cost function, the j will value will be, j of theta will become 1 by 2m. Summation phi is equal to 1 to m. Then here what we are writing, we have to write h of xi minus phi I whole square. Okay. So, and in gradient descent, what we do, we update theta. Theta of j will it will become the previous value of theta j minus alpha into delta of j of theta upon theta j. Whatever theta, which one, whatever one we are applying. So this was my simple one. Now if you say, because you know you have represented theta as a complete vector, theta vector. So your this theta is representing all theta naught, theta 1 till theta n. And similarly at this point also it is representing your all from theta naught to theta n. Okay. Now tell me, like if I am having some equation of theta of x, if I am having something as theta naught plus theta 1 x1 plus theta 2 x2. So what will be the my gradient descent rule? I have to update this theta naught.
Yeah.
Okay. Then I have to update theta 1 and theta 2. Like instead of single variable, we had 2. So if I am writing it like theta naught minus alpha 1 upon m summation of your I is equal to your, it will become from 3 whatever m we have till m, it will become, and it will become h of theta xi minus yi into x naught. If I am writing it in form of x naught, just take x naught form here. So it will become your x naught, x1. And is it clear? Can we write in this way?
Yeah.
Okay, so similarly we can take how many thetas we have. If it is still n, we can write it in this format.
Yes.
N minus alpha 1 upon m, then summation of hx minus y whole square into x of n. We can write it.
Yeah.
So what we do, instead of writing all the equations separately, for notation we write it as like this: theta of j can be equated with theta of previous j minus alpha 1 upon m. Then it will become your summation from I is equal to 1 to m h theta xi minus yi of x of j.
Isn't it xj?
Where?
That h
Yeah, you can write it at, in that case we have to write it as this summation of, internally also we have to keep all the j value. If I am writing it with j notation, then here I have to equate with for j also. Like you can write just instead of this complete x of j, you can write simply xi. Okay, so with notation it will be same. Instead of because for all j we have to do the summation, so instead of that we can just simply write this thing, simply x of I. Hello, Amal.
Hello.
Yeah, so what I'm saying,
Hello.
yeah, you are audible now. What I'm saying, if you have to write the j term, then you have to add the summation before. Otherwise, you can just write it with x of I. Like that is meaning that you are keeping all the, representing all the xj together in a single x, as we write for any other vector form. Like we all theta, for just theta will my represent theta naught to theta n. Okay.
Okay.
Yeah. So now coming to the next part. This you understand now, like our theta will be updated in this similar fashion as we did for single variate. Hello?
Yeah.
Like this is the same thing we did in single variate. It's just that we are we are taking all the theta updating, and then at this point also our all xj, it will be multiplied with all the respective xj value.
Yeah.
So now coming to different part, like but like just assume we have this data, my square feet, which take it as in of 1000 values, 1000, 2000, something like this. Okay, then I had another variable, number of beds. So it is like 1, 2, 3. Then similarly, okay, just for now, let's take this some edge. Okay, edge can be 100, 30, something like this. And then we have price here. So you can see my square feet is ranging is generally of thousands of terms. Okay,
Yeah.
in thousands of digit. Then my number of beds is just a single digit, like 1 to 10, and it is from assume like it is from 10 to 100. Okay, so and in our equation it will be like something h of theta x will become uh, theta naught into 1 plus theta 1. And if I am just taking the first example, so it will be like writing the 1000 similarly plus theta 2 into 1 plus theta 3 into 100. Okay, if I am representing x of 1. So the problem is here, like my this feature is in thousands of term, this is in hundreds, and this is in single. So if I'm plotting, like just assume if you change this theta naught small value, this will be, this change will be large.
Which one?
Wait, we have this theta 1 into 1000 term, then theta 2 into 1, then theta 3 into 100. Okay, now if my theta is, all theta is 1. Okay, so what will be this value? This will be 1000, then this will be 1, this will be 100. If I am keeping all theta as 2. So what will it become? It will become 1000, then 2, then it will become your 200. So in for this feature, the difference is like if I am writing the difference between both theta values, so this will result in 1000 value. This will result in just single and then here 100. And what we do, we update theta in each iteration. And that's why, like, what happens if we plot it on that cost and theta plot, so my one theta will with small variation only, j will be very much. If I am writing this theta 1 and theta 2, so it will be something that j cost will be something like this. Okay, because with small variation of theta 1, there can be large variation in cost function because it is affecting, like, with having the
I didn't really understand that.
How theta 1 and theta 2 are related?
Okay, so mm,
It is supposed to be J theta and
see, we have this data now. Okay, where my area is converting is in thousands of value. The number of beds is just a single digit.
on.
You are not audible, Amal. Hello. Hello, Amal, you are not audible. There is very much voice breakage. Hello. Can you write it in chat?
Hello?
Yeah, it's audible.
Hello? Hello? Can you hear?
You was audible in between, but then it's gone now. Hello, Amal. Can't listen you. Hello. Amal, you are on mute.
Yeah.
Yeah.
Hello?
Yeah. Hello.
Okay. Can you hear me now?
This same problem little bit.
I was just wondering. Can you hear me now?
Yeah.
Can you hear me?
Yeah, I can hear you now. It's. Are you saying anything? Amal, you are not audible. Hello. Hello. Hello, Amal. Amal, you are not audible. Hello, Amal.
Hello?
Yeah, Aman,
Yes.
yeah, you are audible now, I think. So, what was your question?
How did you compare theta 1 and theta 2?
No, let's see. What we do, we have the data set, and for this, how we can write our hypothesis. We can have total in total. We will be having four parameter. One is the bias term, then a parameter for square area, that is, then parameter for number of beds and parameter for edge. And
Mhm.
all those parameters we have to update. We have to update theta 1, theta 2, and theta 3, so that my cost will be
Constant.
minimum.
Yeah.
Okay, so for to find this minimum cost, we have if we are updating theta 1, theta 2, and theta 3, so with very small change, like my theta 1 was multiplied in digit of some thousands. Okay, theta 2 was multiplied with digit of 1, and theta 3 was multiplied with digit of hundreds. Correct?
Yes.
So just assume we started with all values as theta 1. Theta is equal to, we took all this theta 1 as 1, then theta 2 as 1, then theta 3 as 1. So what will happen? We will get this theta 1 into that term, like first term. My this term will become 100, then this will become 1, and this will become 100, like, okay, this is 1000, 100, and 1. If I am taking theta is equal to 2, so what it will be? It will be 2 into 100, that is 2000. Then 2 into 1, 2, and 2 into 100, 200.
Yeah.
So you can see with change in theta is just for single digit, but here that complete this term, like this complete term, this complete term, this complete term, are changing in different fashion. Okay, this is changing in thousands of this is changing in just single digit, and this is in uh, 100 of values. Understood?
Yeah.
So with small changes theta only, there is much difference between in the changes of my features, that complete
Yes.
theta into feature term. So because of this, what happens? Like this will give me some cost value. This term will give me some cost value. This term will give me some cost value. So what happens? Like if we don't have features in proper scale manner, like in some same similar range, in that case I get the contour plots something like this, like with this theta, this small theta,
Shouldn't
and
it be theta 1 x1?
what?
Shouldn't it be theta 1 x1 and theta 2 x2? Because
No, what you remember, we were making the contour plots on basis of theta and j. Our at one variable was my theta, and on parameter we were making contour, and we were getting something
Yeah.
like this. Okay,
Yeah.
so this was my the j term, and with the variation in theta, like this one was theta naught and theta 1, so I was getting some j term, and we made the contour for that. This is j, and it was something of ball shape, and if we flatten it, like if we were making that on 2D, so this was my contour plot. Okay, so I am doing same thing. I am telling that if I am having of value of different ranges, so with small changes theta, the multiplication term theta 1 x1 or theta 2 x2, this term will be changed differently.
Yeah. But here you're only comparing theta 1 and theta 2, right?
And this is
Not
like
theta 1 and 2.
just
So
what pardon?
the value will change significantly if you're doing theta 1 x1. Say
Yeah.
if x is 1000 and x1 is 1000 and x2 is 1.
Huh.
But here
So this is
x is
my
not there, so yeah.
this is my j of cost function. I'm telling about the cost function, how it will, the plots of cost function will be similar to this one. If I am, see, one plot I can have is like this. Okay, this is what we yesterday we were discussing. Like our plot was similar to this, not similar to, like this was ellipse only, but the change was proportional, like changing theta, and the plot on theta naught and theta 1 was similar to this. It was not elongated or something. Just see two plots. Okay, one plot is this one and other plot is this. Can you see the difference? What's happening? Or take it. Can you see the differences between them?
Yeah.
Like in this, with take it theta 1, theta 2, then theta 2, theta 1, theta 2. And this is all about the cost function. The plot is for the j of theta x. Okay.
Yeah.
Just 1 minute. Yeah, sorry. So when we have the theta and the two parameters in different scale, the multiplication, these term is on different scale. So what happens that we can get plot like contour plot like this, and that variation in cost can be of similar to this value. Hello?
Yeah, but how is there a relationship between theta 1 and theta 2?
How is the relation?
Yeah, how is there a relation?
Wait, I will share you yesterday's PPT. Okay, 1 minute. Yeah, yesterday when what we were doing, like my cost function, yeah, when I had only single variable, so my plot was a theta naught, theta 1, and then cost of that. Okay, cost function. Then in that way, when we plotted the cost function with relation of my parameter theta, so I was getting the ball shape graph. Okay.
Hello?
Yeah, you remember this one?
So this is between J and theta 1.
Yeah.
Right.
So
J and theta 1 I understood, but not theta 1 and theta 2.
I will go in.
Yeah.
So here we had the single parameter in our function. So we were just plotting it with a single parameter and the cost function. So this is 2D plot and we are getting ball shape function.
Yeah.
Okay. Now when I had two theta value, like if I am writing my hypothesis function as theta naught and theta 1, so I am having two parameters. So it was coming like this, like at one axis there is theta naught, another axis theta 1, and then here the ball shape figure is my cost function.
Yeah.
Remember this one?
Yeah.
Then to simplify this plot, what we did, instead of plotting it on 3D, we represented it on 2D using this plot.
Oh, okay, yeah.
This is my contour. This is called the contour plots. Okay.
Yeah.
So same thing, this is what I'm saying, like here my theta not, the change of values, the contour plots are not like they are in some proportion manner. Wait, I will show you that. See, like you can see the difference between this one, then this one, the contour plot plot, there is difference between the thetas. This is that same plot. I am telling like there can be different scenario. We can get plots in different manners. See, we are plotting it on theta naught and theta 1. So just we can write it on like even you can take here also. You can take theta naught and theta 1. That's not a problem, but it can be in different shapes.
Yeah.
Okay, shape can be different depending upon the value of theta naught, theta 1 and its relation to the cost function. Okay, so is it clear now, Aman? Hello?
Yeah.
Okay, this is
Yes, it's clear now.
this is this plot only. So what I'm just telling that it's not necessary that always this plot will be of this shape only. It can be of different shape also. Okay, it can be of different shape also, where my proportion is properly proportionated, where I am having very large with very small change, this value is changed, cost function is changing. So see, the shape of the plots are different. So I can get this plot, and why this happens? This happens because the different range of values, different range of input value. Because of this different range of value, it happens. Now, there is one problem with this. Okay, I will tell you in next few slides. So, what we actually want always, we want to have my cost function relation with parameter in this way. Like the proportion should be proper. In this proper proportion, this I can get, and this I always want, so that my gradient convergence will be in, like it shouldn't it shouldn't be like that I am running it for 100 of iteration and then I am getting this value. Okay, so if I in this plot, what can happen, like you can have to run your algorithm for thousands of iteration. Iteration is the each update rule one. Okay, and at this place I can get it in 100. If I have the plot in this way, I can get it in 100 of iteration, and here it can take the thousands of iteration. So that's why we always want it to be of this shape. And how we can get this shape? We can get this shape if I am having my all the features value in some similar range. Like if I am having the square feet in some 10,000 to some 1,000 to 10,000, and then your age is also in I'm having age in 100. So what we do, I will take this square feet and I will convert it in this format. Then I can convert it in this format. Like the only value I am changing, I am keeping the proportion same. Understood what I am trying to do?
Yeah.
What I'm like, I had this age feature. Okay, my age feature was of ranging from 100 to 10, from 10 to 100, and my square feet was ranging from thousands to 10,000. So to make the new age feature of same proportion, like same digit range, I am trying to convert this square feet to the new square feet value, and that is ranging from 10 to 100. Okay. See what if you take any range, if you take any two values, if you get some 100 marks out of 100 and your friend got 80, okay, and you have to represent in the 10 this is of percentage 100% and this is 80%. Now it can, the total marks can be of 100.
Yeah.
It can be, if I'm telling that 10% you got the 100%, then I am telling okay, this is on base, if I'm taking in 100 number you got the 100. But if I'm saying the total exam was of 10 marks, so this means you got 10 and this person got 8, so the relation is same. Okay, but only the digit is changed. Here I'm using just single digit, here two digits are used. Okay, so same thing I am doing here, the relation will be same. Like if a house is of thousands of square feet, so here it's 10 which is lesser than 100 square feet.
Yeah.
Okay, so it is called actually feature scaling. And why this why we do feature scaling? To get plots of this manner. Okay, yeah, so in that case, like if I'm having the features of higher square feet, so I can write it something like that. My x1 was my x feature, so I can say that okay, I will decrease that square feet, I will divide that it with thousands. So what will happen, wait, I will write it in this. Yeah, so to make the square feet of this value, what I have to do, like how we got this, if I'm dividing the square feet with 100, and similarly at this place also it is 100, so we will get this value of the range 10 to 100.
Yeah.
So like in generally what we do, we try to range our feature in value of -1 to +1. Okay, like if I am having some negative feature, so it will be represented in range of -1 to 0. Okay, and my positive feature will be represented in range of 0 to +1. So, and in this case, I can represent in this 1 to -1 to 1, and this also in -1 to 1. So here both of the scale will be same. So I can get this contour, this proper contour plots. And this we do to decrease my training time, to decrease the number of iteration, or you can say to converge my algorithm fast.
Yeah, okay.
Okay, so there are actually different, and before going to that, it's like you can see here, this range is very much different, and if you are converting this -1 to 1, like converting h from -10 to -1 to 1 is not, we are not doing much change. But if we are converting square feet to -1 to 1, we are doing a lot of scaling in square feet feature. Correct? Hello?
Yeah.
Right? So generally what we try to do, you can convert age to -1 to 1 easily, but we try to use something like, if you are having many features of some 10 to 100 or 1 to 10, so it's better to convert all to -1 to 1. But we also try to avoid converting from thousands of 10,000s or million ranges features to -1 to 1. We try to convert, like we can convert it in 10 to 100. So this will be better than converting in -1 to 1. Okay, so it's not a hard
Hmm.
rule to convert all the features, scale down to all the features to -1 to 1 only. It depends on the what is the range of feature we are using. Okay, you can have x in range of -10 to 10 also. That's not a problem. But it's always what we always try to do. We try to convert features according to their range, not converting very large feature to lower number. Or if I am having something 0.0001, if I am having feature xj, okay, 0.0012 something 0.00003, so it's not advisable to convert it to this range. Similarly, if I am having something of 10,000s to 5,000s, so it's not advisable to convert it to this range. Instead of that, convert it to some range of something similar to 0.001 to 0.003, something like that. Okay.
Okay.
Okay, so there are actually different methods of feature scaling. One is called normalization. That is actually normalization only. Like one is normalization, one can be min, max.
Wait, Miss.
Huh? Hello?
Is it fine if you can take a 5-minute break?
Yeah, okay, fine. Then we will start. Yeah, okay.
All right.
Okay, you can just like drop this call and connect again. Whatever you are comfort.
Okay.
Okay, bye bye. Let's
All
meet
right.
after 5 minutes.
All right. Yes.
Hello, Nimai sir. Hello, Nimai sir. अरे
Hello.
Yeah. Can't add more seats now. Okay, I will clear this. All the things are clear now because I will be deleting this seat now.
Yeah, except when will it go to minus?
Huh?
You said
Previously, -1 to 1 also can happen, right? -1 to 0 in that range.
That will be in min max.
Min max, okay.
Yeah. Like actually, when we can take any range, I will show you that value. I have for you. I have shared this. Share. Yeah. Can you see my screen?
Yes.
Yes.
So this is the equation. So you can make any ranges. Okay. You can have any ranges using this equation. Here the min A is the actual minimum which you want, actual maximum which you want, and the new max is the maximum range what you like. If you want to convert your data from -3 to 3, so in that case new max will be 3 and the new min will be -3, and we need the actual min. Okay.
All right. Yeah.
Okay. Okay, clear all the things. Okay, so
Have you thought about this overfitting and underfitting?
no, it will come later in later like actually the after the logistic regression that thing will come.
Okay, so today what all course you are going to take?
Now, I will tell all the things related to linear regression. Like the single variable is completed, so multiple variable will be completed in some time. So after that, we will take some break, and then we will start for the logistic regression.
Okay, so logistic regression you want to take or I will take?
If you can take, then yeah, that will be better. That will be helpful for me.
Okay.
Okay.
Yeah.
Okay, Aman, so now we will see how gradient descent is working in the practical scenario in multiple variable case.
Okay.
Okay. So you have understood that how we are doing the gradient descent in single and multiple variable case. So now we have to see whether it is actually working or not. Okay. The one thing is like we want j of theta to be minimum. Okay, this is our loss, or you can say cost function or loss or your error term, whatever, and our goal is to minimize this value. Okay. And for that we update theta, this theta parameter we update it, and we check the cost value, and then if it is going down, we say it's lowering. So to check it in practical scenario, what we do, we plot the cost function, okay, j of theta, on basis of iterations.
Iteration, as in?
Yeah, iteration is the number of times we are updating this theta. Hello, Nimai sir. Nimai sir, can you please mute? Okay, yeah. So number of iteration is the how many times we are updating theta to get the minimum j value. So in general, what happens, like you will be getting some plot like this, and if you, this is the actually the correct plot which we want. Like in start, we will start with some random value, so a random value of theta. So at that point, we will be having the higher cost function, cost value. And when we are updating the theta, and next time when we are calculating, so we will like to see like our cost value should decrease. So like here, if you 5 iteration, then 10 iteration, then 100 iteration, so every time you, what we want to decrease the cost value. Okay, so at this point theta will be some theta 0, and this is like complete theta. Wait, I will change the notation. Uh, this is at theta I is equal to 0. Okay, then here the theta value will be on I is equal to 5. Then at this point, this is theta of I at I is equal to 10. Okay, so similarly, as we are updating the theta, we will be getting cost function, and what we want to be it like the decreasing curve. And at some point, what will happen, like when it reaches this contour position, when it reaches this location, so in that case, it won't be decreasing much. Like either it will be constant or it won't be decreasing. Okay,
Wait,
this is contour plot. Contour.
I didn't really-
Okay.
We started at some point, like we started at here. So we've gone little bit, then this, then this, then we reached here. So when we are reaching at this location, so that is the location where we are getting the minimum cost function. So either it won't be converging, or there will be very little step here, here only, and coming to this place only. Okay.
Okay.
So this is the case when we say our algorithm has converged, so we don't need to do any more update.
Okay.
Okay, so by the plot we can say, okay, at this location we have converged, so we can just keep number of iteration as 200 for our algorithm. Okay, but how any system knows when to stop? So for a system, there is a fixed thing, like either you can just tell to converge at this particular 200 steps, or they can they what they do, like they see what is the cost function, cost at 201, like at each step, then cost at 202. So they will be getting some value, some here 199. Okay, when this changes is with difference of minus 10 to power 3, like when after 203, if it the change is like 89.0003, then again at 204 it is 89.0001. So you can see the changes is very minor change. Correct. So this means that at this step we have to stop our algorithm, otherwise we are just wasting our time and the resource.
Okay, then how do you find the lowest cost then?
Yeah, there's two way. Either you see this plot, or you can use this difference checking, like check cost value at iteration I, then I plus 1, then I plus 2, and see whether the difference is lower than some threshold. Like you can take this threshold, or you can, for depending upon the your algorithm or your use case, you can take the difference, or you can take the threshold as 10 to the power minus 4, and at that point you will stop.
Okay.
Got it, or should I tell you on a new slide?
I think just repeat it, that last part. Yeah.
Okay. Wait. So, So, what we can do? See, we don't know. We can't plot counter plot without running the algorithm before itself. Okay. So, what we do? We plot cost function with iteration.
Yeah.
Okay. So here you can see my cost function is decreasing, and at this point, it is somewhat not changing much. It is like this. Okay, so why to run like why to run do these many iteration extra when we already got the almost near to minimum value at this point only.
Okay. Yeah. Oh, then you just take that point. Okay.
Yeah, like like okay, if I'm stopping at this point, I am losing like my cost function. I could have decreased it still here, or if I'm stopping in there, still it's decreasing. So uh, we can go till here. Okay, now but at this point it's almost there's no change, or either very minimum or completely no change. Then why to do these many process extra, why to run these many
Yeah.
times extra? So that's why one thing is like you can using the just plot curve. Okay, just the with iteration, using that time only with plotting, you can say when to stop, or you can tell that if when my difference between my cost function is 10 to the power minus 3, like if I'm at 200 step, if I'm getting some cost function as 100, then at 201 step I am getting cost function as 99.00004, then again at 202 if I'm getting
Wait, and
99.0003.
one doubt. That iteration, is it theta 1 or theta 2 or it's all of them?
Iteration is like if I'm having just single variable, if my function h of x is x1, theta 1 and x1, so in this case we have just single parameter. So what we do at time is equal to 0, we will find it, we will update theta 1 at time is equal, then again at time is equal to 2, we will update theta 1, again at time 3 we will update theta 1.
Okay.
Okay, so this means like if I am doing updation only 3 times, this means I am doing the 3 iteration, and again if I am doing this iteration for 100 times, that means I am like changing it, then I am doing 100 iterations. This is how many times you are updating your theta. Okay.
Yeah.
So this is clear, like this is actually like manually you can see this, you can tell to your, you can make a in write code only, you can write this step to check the changes. You can tell the threshold, it can be either 10 to the power minus 3 or minus 2 or minus 4, like depending upon the different scenario, different data and problem, it can, you can change the threshold values.
Okay.
Okay.
Yeah.
So actually like why these okay, no problem. So see, actually what happens, like sometimes we can get cost and iteration plot like this. We can get it like this also. That means my, whenever I am updating my theta, the cost value is always increasing. Okay, but what we want, like I want my cost function to decrease with iterations. Like whenever I am running and I am updating, my cost value should decrease, it shouldn't increase. Okay, or sometimes this also happens, like it can go like this. It will decrease, then increase, decrease, and increase like this. Okay, so why this happens actually, when you go through this plot, the bowl plot, which is the parameter theta and the cost function j. So what we do, we take the step to lower down, we take step like this to reach here. Okay,
Yeah. Yes.
and when we have the last steps, in that case what happens, we reach here, then here, then here, then here, we go like this. So what you can see, like in this case my cost value is increasing instead of decreasing, because due to the last step it's increasing by the number
This is
of.
that learning rate, like that alpha learning rate.
Yeah, this is the because of the learning rate. If my learning rate is high, is very high, so in that case these two cases happens in that time. Okay, so that's why it is advised to keep the learning rate low. But there can be one case this also, like it can be this case also. So in this case you can see there is very slow decrease in the cost function, correct?
Yeah.
So it is advised to take that alpha which doesn't make your curve like this, neither like this or this. Okay, it should be something like, initially actually what happens in practical scenario, initially there will be large decrease and then it will be slow. So whenever it started to slow down, we like started to converge, we stop it at that location.
Yeah.
Okay.
Yeah.
Okay. Now coming to the next part, how you will decide which alpha to take. Assume you are running algorithm. You started with alpha value something of 0.001. You thought, okay, we should take this small value. Let's take small, and you started with 0.001. Okay, then your curve was something like this. Now you thought, okay, let's change alpha, and you changed it and you use this value.
Yeah.
So you got the curve something like this. Now you changed alpha to 0.1 and you got the curve like this. Okay. Now you change the value of alpha to alpha is equal to, you kept it as 1, and now what happened, it started to increase. Alpha 10, again it is just make for better, take this one, it was something like this, and with 10 what happened, it exploded. So you can see, like if they are with a different value of alpha, you are getting these plots. So in that case, which value you will take? Alpha, 0.01, 0.01, 0.1, 1 or 10. Which one you will take? These three?
Yeah. Yeah. Because it's going down.
Which one?
I think
See,
point
these
zero,
two,
point 001.
no. These two you can directly reject, because here instead of decreasing the cost function, it's increasing.
Yeah.
Correct. Now let's see on these cases. So see, at this case you have it is decreasing little slow. Okay. For 0.01, it's decreasing faster than the above one, but the decrease is more than the below one. In this case, it is decreasing than this one, but it is not increasing also. Okay, it's always decreasing, and it's decreasing fast enough. So like here at, just assume it is some 1000 iteration, this is 700 iteration, and this is some 400. At this point it is some 400. What you will prefer? You will prefer to get the best algorithm in less time. Okay, so yeah, this is fulfilling your criteria, so that's why you should try with different alpha value, and then take that one which is not very which is higher value, but which is not increasing your cost function, like that. Like at this place their cost function is increasing only, so that's why always take that alpha value which is not too low, like this, where our learning is slow. Instead of that, take that value where learning is fast, the decrease is fast, but it's not increasing. Okay.
Oh, okay. But why for 1 and 10 it's increasing?
This happens now, like if the cost function actually with relation to parameter and cost function, when we take the larger step, it goes up, like the cost it can be at this point, then it can go to this point, like this it can go this point. So this is due to the large value of alpha, your change in theta will be very much, and you might skip your lower value. Okay.
Yeah.
Okay. So now we understood how to scale the feature. Then how to scale the today we saw the for multiple variables, then the importance how the gradient descent is working for multiple variable, then how to do the feature scaling, and which alpha to choose. Clear all things? Okay, so let's go to the next step. This actually when you have a house, okay, this is the road, and here your house is, like some houses there. Okay.
Yeah.
So for this house, you can see for this area, there's its length. Okay, and then like, or you can say it's the front of it is the front of house, and this is the width of house or depth of, whatever you say. Okay.
Okay.
Okay, this is depth. Okay, and this is front. So at this place, what information you had? Your data will be of front, then depth, then its price.
Yeah.
So in this case, if you take the simple linear equation, your hypothesis will be h of x will be okay. Yeah. So Amal, yeah. So in this case, our equation will be this. Okay. But it's not necessary to use only these features only. Okay, we can say that from the front and depth I can get the area of house. Why not to use that feature? Correct?
Yeah.
So like if you make your data like this, from that you calculated the area and you had the price. So this is theta 1 plus theta 1x. This is this function, and like you might remember, like we were talking where house price was something like this. It was if this distribution. Okay.
Yeah.
You can see this line. If you take a simple line, any line won't fulfill your proper prediction. Just think of any line, whether it is fulfilling your requirement to get to know all the house price relation.
Mm, I don't understand what.
This is my area. Okay, this is price. My data is distributed in this way.
Yeah.
Okay, if I take a single line, just think I took this. Is it telling me correctly the relation with area and price?
Yeah.
It's not telling, no?
Yeah, it's not telling.
Because it just like if you have the area of this area, so it will say this price. But actually, for this area, these are the data points which are telling the actual price. So the price was much, but you have predicted the lower price.
Yeah.
Okay. Similarly, if we just take some other line, just take this line. So in this case, like if you go to this, okay, this house, if you go for this house, so it will say the price is this one, but actually what its price should be something near to this.
Yeah.
So if you take, can you approximate this data plot with any function, single line function? No, like even you take this,
No,
no one will tell you
suppose.
the actual values.
Yeah.
But if you have the function of something similar to this, so it will tell you approximately, for all it will tell you, okay, the approximately correct value it will tell.
Yeah.
And how we can get this one? If we have to use some other polynomial equation, then only we can get this curve from with the this single equation we can't get, whether it is a multiple variable also we can't get it. Okay, single line. But if we have something of other term, in that case we can get this value, this curve.
Yeah.
Am I clear? So
Yeah.
just assume you are writing some equation like this: theta naught plus theta 1x plus theta 2x square. Okay, then
Yeah.
or you can write it like, you can make approximate any function like this also: theta 1 x1 plus just considering only one equation, one variable. You can write something of this also. You can think like, why to just fit it with single line? You can fit it with a polynomial curve also. Okay, so we had the size value, so you can say I can take the size, then square of size, then cube of size. You can take any value. Okay, so now you can have function like this. Your h of theta x can be theta 1 and theta naught plus theta 1 into size, then plus theta 2 into size square, then plus theta 3 into size cube. Okay, so why we actually use the polynomial function is to this purpose only. Like if my data is not properly fitted with a single line, so then let's go to the polynomial variable. So in this case, I can write it like this also: theta naught plus theta 1 x1 then plus theta 2 x2 x3, and now my x1 will be size, x2 will be size square, and x3 will be size cube. Okay, we can write it like that, the above equation in this fashion.
Yeah.
Okay, so now there is one problem also. Okay, if you are doing the cube or square of size, so what will be the values in this case? You already have your sizes of something square term, thousands of term, and if you do the size of square, so it will become your 1000 into 1000. Okay, then the cube term will become like this. So to avoid this expansion of the values, what we can do, we can take this as like this also, h of 2 theta naught plus theta 1 into size plus theta 1 into root of size. Okay, because see, we just have to make a function so that I can predict my data point accurately. And when you look for the square root, how square root goes? Initially, it will be like this. Then it will be something similar to this. This is the curve of square root function.
Yeah.
Okay, so that's why you can make the different polynomial functions also for linear regression. Like it's not always just you have to take the linear term also, only you can take the non-linear term also to make your data proper fitted.
Okay. You have to square the values, right? Square and cube it.
Yeah, like you can take the square cube also depending upon the nature of your data, like what is suiting your data more. Okay, like if I am having some range of some 1 to 10 value, so in that case what will happen, like if there is value 2, so it will be 2, then 4, then 16, so no 8, 2, yeah, then it's not much difference. So here there is no problem taking the cube root or square term, but in when you have values in term of 1000, so in that case the value is very much exceeded, like it's of the 10 to the power 9. So in depending upon the type of data, you can take which actual functions to use, like to use the square term or the square root term. Okay.
Yeah.
This is actually to make like include the non-linearity, to learn the non-linearity of data.
Yeah.
Because it's not like data can be of these two, like it can be both cases. It can be this, and it can be this. Okay, so this is not this is not linear, but here the data is linear. So here the linear equation will work properly, and in this case non-linear regression will work properly. Okay.
Yeah.
Okay, now coming to see, actually till now we learned how to update theta using the our main goal was to get the theta where my cost function will be minimum. So for that we use the gradient descent approach. There is one more approach. Using that you can find that theta is the normal equation.
Okay.
Okay, and what that equation says, like how we can find it in this equation, the value, the equation is just only theta is equal to x inverse xt into y. Only using this equation we can find this theta, okay, in single go. Now what is my x and all? Okay, so if I am having some data like this, size, take it as 2014, 2016, 2017, then number of beds 3, 5, 4, 5, then age of house, it is 30, 40, 10, and this is the price. $1,000, $200, $10,000. Okay, this is the data. So in this case, my X will be input matrix plus bias term. You remember bias term? How we make that function of X is equal to theta naught x naught plus theta 1 x1 plus theta 2 x2. Okay, we have three variables, so one more will come, theta 3 x3. Okay, so and my x1 x0 was always 1, so 1, then 2014, then 3, then 30. Okay, then similarly here it will be 2016, 4 and 40, then 1, 2017, then 5, then 10. Okay, this is the representation for x. And how we will write y? So for writing y, we can write it like this. Your y will be a vector 100, 200 and 1000. Okay, and using this x and y, you can find your theta value using just this simple equation in a single go. Okay.
Okay, but
How do you find the y again?
Y is your this is the given part. Okay, this is
Okay.
the given value. Like what we do, we want to find the theta. For finding theta only, we run gradient descent algorithm.
But is this theta 1 or theta 2 or?
It will give you complete theta. It will give you this theta matrix. This is like
okay.
theta matrix. This is like.
मैं थोड़ा सा इसको समझा दूं अर्पणा, अगर तुम चाहो तो मैं थोड़ा सा समझा सकता हूं, ठीक है? ये वाला how the theta equation is coming, I can try to help.
No, like I think for now it will be more, so better let's take it in the next, like last lectures when we have the time.
No, because this I will be reading in this one, no, logistic regression.
No, I don't think you will need.
Okay.
Yeah. Like I am telling, whatever is required for the next lecture, that I will be.
No, if it is required, then I will tell this one. No.
Yeah. Okay. So this is the theta. Okay, and using this x and y, you can get from this equation, you can find the value for the theta, whether it is 10, 0.1, 20 or whatever it is. Okay. Okay, so this representation actually, I will tell you more because this will be used. Our examples, whatever we have, if we have the m example, okay, it will be x1, y1, then till xm, ym. So I can write xi as x0 I then x1i till xn I. So here my n is the features. Okay, n is the feature value. Like if I am having 4 features, so it will be till 4, and this is the data point. Whether it is single first point or second point. 1, 2, 3. This is the data point, and take it as m, and the features, and this y. This is n. Okay. Sorry. This is n value, number of features, and m is the number of data point we have. And to represent each point, we use this notation. X of I means x of data point 1. If I am saying x of 1, then this will come. Okay. If I am telling x of 2, like for x of 2, I am saying this one. Okay.
Yeah.
Okay. So now, and how we are writing, like when I am using the vector form, I use this representation. This is a vector. Okay, which is my 1 cross n cross 1 matrix, you can say. A vector will be here, your n cross 1 matrix, which is a 1 data point. So to write it in complete, for complete vector, we write it as x1 transpose, then x2, then x2 transpose. This is my complete vector. Then xn transpose. Okay. Understood this representation? This is called design matrix. Amal?
Yeah.
And my theta is x transpose x of inverse into x transpose y. Okay. Is it clear? This design matrix representation and theta equation is clear?
Yeah.
Okay. So let's go to the next part. Yeah. So now we have got to know how to find theta using 2 methods. One is gradient descent method, and another is normal equation. Okay. So there is actually advantage and disadvantage of using those methods. Okay. So if you are going through gradient method, what you have to do? You have to choose alpha. Correct? Then in gradient descent method, because you have to choose theta, you have to find theta. So for that you need to take iterations. Correct? And okay. In normal equation case, you need to choose alpha? No. Do you need iterations? No. But you just have the theta equation, and using that you do your calculation, only this equation. Okay. So you don't need to choose alpha, you don't need to do the iterations. But there is one problem. Your x, when you say x transpose into x, so what will be its dimension? The dimension will be n cross n. Correct? See, this
Yeah.
is x, and when you make the complete x matrix, So it is like all the features. Okay. So till here, this is the n, and this one will your m value. Correct. So,
Yeah.
and if you multiply this 2x, so what it will be? It will become your m cross n. Yeah, just 1 minute. I'm writing right now. Yeah, this is actually +1. I forgot to write. Sorry. So this is your m cross n plus 1 into your m cross. This is a transpose. So this is wait, for the transpose. It will the sign will convert. So this will be your n plus 1 into m matrix. Then again you are multiplying m cross n plus 1 matrix. Okay, so the multiplication of these two matrices will give you of size n plus 1 cross n plus 1. Correct?
Yeah.
There they haven't considered that. Okay, and just because of this n, you can actually tell this is the order of n, but like let's not use the ordering word because that is will be confusing for you. So the size will be of n cross n. Just imagine if you have thousands of features, what will happen? Your size will be n cross n plus 1 cross n plus 1 will be your 1000 cross 1001 into 1001 feature. Like this will be the size of your matrix. So and when we compute this value, like when we do the normal equation with these many features, it is very computationally inefficient for a computer. Okay, like it will take a lot of time for this computation only, and computer with system will need lot of space also. So that's why when we have the large many features, in that case we avoid using this normal equation. Okay, so the disadvantage for this is large feature. Like when we use this one, we use this for small n. Small n, in that case we use, and for this we for whether it is small n or large n, we can use this anytime. Okay. For any n, there is no problem.
Yeah.
Yeah. So this was actually is like the complete linear regression. Okay. So is there any doubt?
No, I think it's a fine. Yeah.
Okay. Okay then.
Wait, I just wanted to ask, these videos, where are they going? Are these videos being uploaded somewhere?
Yeah, Nime is recording this video. So like, wait, I will ask him. Okay. He can share it with you.
Okay, that will be good.
Okay. Okay, Amal. We will take some break so that Nime can get ready and start. Okay.
All right. Okay.
Let's meet after 10 minutes. Is it fine?
Yeah, 10 minutes is fine.
Okay. Bye bye, Amal.
All right. Thank you so much.
Welcome. Hello, Nime sir. Hello.